Hey everybody, Dr. A here, and in this video we're going to be exploring an example of using deflection formulas. So let's go ahead and get started. In the given information, we're being asked to compute the maximum deflection, and we're being told that the modulus of elasticity of the beam material is 29,000 KSI, so that's steel, and we're being told that the moment of inertia is 250 inches to the fourth. So here we have a simply supported beam with a point load of 500 pounds in the middle and a uniformly distributed load over the entire length of 0.1 KLF. And so how do we go about this? Well, again, we want to use the deflection formulas that are applicable for these loading cases. The first thing we want to note is that by superposition, this can be rewritten as the following situation. We can rewrite this figure as a simple beam that's 16 feet long with a uniform load of 0.1 KLF. Let me move that 16 feet down a little bit. .16 and then we can add its effects to a simply supported beam with the same geometry. There's that 8 feet and 8 feet with 500 pounds right in the middle, okay? And so what we have here is the idea of superposition. So we're going to have this deflection diagram from the uniform load, and the maximum deflection, of course, is right in the middle. We're going to call this delta 1, and then we're going to have a deflection diagram. Let me draw that a little bit better for us. Nice and smooth and symmetrical, unlike my bad handwriting. We'll call that delta 2, okay? And so the overall maximum deflection of this entire beam here, call this delta max, will be equal to delta 1 plus delta 2, okay? That's the idea of superposition. So we can write delta max is equal to delta 1 plus delta 2. So where do we get these pre-derived formulas from? Well, you can find them in most mechanics of materials textbooks in a table somewhere. If you're looking at the Hibbler mechanics of materials textbook, this will be found in Appendix C. So you want to find the equations for each of these two load cases, okay? So if we look at the load case of the uniform load, all right, that formula is going to be equal to negative 5 WL to the fourth over 384 EI, okay? And we're going to add that to the deflection formula for a point load at the midspan of a beam, and that's going to be equal to negative PL cubed over 48 EI. So what I would encourage you to do is pause the video and maybe go to a textbook or go online and find where these formulas are coming from. Don't just trust me right now. In fact, I'm looking at a book right now, okay? So find this in your textbook and make sure you know where these formulas are coming from. Now, what do these negative signs indicate? These negative signs indicate a downwards deflection, okay? So you can keep them there, or we could eventually do away with the negative signs and put like a little downward pointing arrow, all right? So how do we combine these together? Well, we substitute these values in. So we're gonna say delta max equals, now I'm gonna drop the negatives and I'm gonna put a downward arrow here in a minute. We're gonna say 5 times W. Now W is 0.1 KLF. Watch your units, please, okay? So notice that E and I have units of KSI, kips per square inch, and inches to the fourth. So I would convert all my units right now before we make a mistake. So instead of 0.1 kips per linear foot, we're going to convert that to 0.1 kips per linear inch by dividing by 12. So we're going to say this is equal to 0.1 KLF is the same thing as 0.008333 KLI, kips per linear inch. Okay, what about the 16 feet? Well, that's going to be equal to 192 inches. And of course, each of those 8 feet is equal to 96 inches. Okay, so I would do all my conversions here at the beginning before I make a mistake somewhere. So 5 times W is going to be 0.008333 kips per linear inch, or KLI, divided by 384 times 29,000 KSI, kips per square inch, and then times 250 inches to the fourth in that denominator. And then we're going to add to that 500 pounds. Now, you're using kips per linear inch here, right? You got terms of kips. So instead of 500 pounds, maybe you should say 0.5 kips. So we're going to say 0.5 kips times the total length, which is, I forgot a length term over here. I hope somebody caught that. So that'll get you the wrong answer real fast. 192 inches to the fourth here. And so back on the second term now. 0.5 kips times 192 inches to the third power, all right, divided by 48 times 29,000 KSI. And then again, you got that 250 inches to the fourth in the denominator. Make sure we didn't forget anything else, because could have had a catastrophic calculation here. Would have been completely wrong. All right, so we're going to punch this in our calculators very carefully. 5 times 0.008333 times 192 raised to the fourth power. And then, we're going to divide that by 384 times 29,000 times 250. And so for that first expression, that first term, I get 0.0203 inches. And then let's see what we get for the second term. We got 0.5 times 192 cubed divided by 48, and also divided by 29,000 and 250, all in that denominator. And so we'll get plus 0.0102 inches. And so we add those two values together, and we should get 0.0305 inches deflecting downward. So instead of that negative sign, I'm putting a downward pointing arrow. Okay, so that concludes, that's our solution. That concludes this example. If you found this helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.